All right, strap in. Let's dive into this mission briefing, rookie pilots. Today, we're doing an interstellar explainer that's going to completely redefine your understanding of scale. We are embarking on a massive quest to really grasp the staggering, mind-bending dimensions of our universe. You might think you understand distance, like a long road trip, but by the end of this flight path, your entire perspective, it's going to be shifted forever.
So, here is your flight itinerary. We're tracking a radial outward trajectory today. First, local system navigational waypoints. Next, the interstellar boundary. Third, cruising the Milky Way. Fourth, intergalactic macrostructures. And finally, the edge of observable space.
Initiating Phase 1, Local System Navigational Waypoints. Right, before we can sprint across the galaxy, we gotta learn how to crawl through our immediate orbital neighborhood.
Now, thinking about everyday travel speeds proves just how totally inadequate standard human cruising speeds are for this flight path. Take the moon. It's about 384,000 kilometers away. If you got in a car, right, and drove at a constant 100 kilometers per hour, you'd be behind the wheel for over 160 days straight. No sleep, just driving. And what if you wanted to fly a 900 kilometer per hour commercial jet to the sun? Well, pack a bag, because that's a 19-year layover. Mars? Depending on orbital dynamics, it fluctuates between 54.6 and 401 million kilometers away. At its furthest, that exact same jet flight would literally take you over 50 years.
So, to avoid our flight computers just completely melting down from the sheer number of kilometers, we need to shift our navigational gears to the astronomical unit. The AU is our go-to measuring stick for local flights. Basically, since the Sun is about 150 million kilometers from Earth, we just call that distance 1 AU. To put that into perspective, light travels at an insane 300,000 kilometers per second, meaning it takes a mere 8 minutes and 20 seconds for light to make that 1 AU trip from the Sun right to your windshield.
But let's push the throttle and go further. 4.5 billion. That is the distance in kilometers to Neptune. It's a waypoint so unimaginably far that even light, acting as our comm signal, takes over 4 hours just to reach it from the Sun. Neptune marks the extreme edge of our immediate solar neighborhood. And honestly, the distances are already getting pretty tough for the human brain to truly visualize.
Approaching Phase 2, the interstellar boundary. This is where we leave the cozy confines of the solar system and hit the absolute fringes of the Sun's gravitational influence.
Voyager 1's trajectory brilliantly illustrates this boundary. It is our absolute furthest human-made scout, currently drifting through the cosmic sea at 17 kilometers every single second. Launched way back in 1977, Voyager 1 is humanity's ultimate pathfinder. As of right now, it has covered a staggering distance of more than 22 billion kilometers. I mean, think about that. It is a silent wanderer that has been traveling out there for over 4 decades.
And despite the overwhelming vastness of the coordinates we're charting today, it's pretty humbling to remember that our entire history is localized entirely to one fragile little sphere. Back in 1990, at astronomer Carl Sagan's suggestion, Voyager 1 turned around at a distance of 6 billion kilometers and snapped a photo. Earth was just this tiny, faint dot suspended in the black void. Sagan famously called it a small speck in the immense universe. It's a sharp reminder for all of us pilots to cherish and preserve our only home base.
So, the absolutely crucial point here is that crossing this boundary, which we call the heliopause, means leaving our star's protection entirely and entering the true void. This is the exact perimeter where the influence of our Sun's solar wind simply ceases to exist. Once you punch your engines through this barrier, you are officially flying in the vast, untamed realm of interstellar space.
Now, as we prepare to cross the Oort cloud, which is this theoretical sphere of icy objects extending an unbelievable 100,000 AU from the Sun, we actually have to upgrade our navigational instruments again, this time to the light year. See, 100,000 AU is roughly 1.9 light years. When distances become this colossal, the AU just isn't cutting it anymore. So we switch to measuring by the distance light can travel in an entire Earth year.
Engaging Phase 3, Cruising the Milky Way. We are now officially plotting coordinates for deep galactic transit. Look at that number, 70,000. That staggering figure is exactly how many years it would take a probe, moving at Voyager's current breakneck speed of 17 kilometers per second, to reach our closest stellar neighbor, Alpha Centauri. Let that sink in for a second. Alpha Centauri is located about 41.3 trillion kilometers away, translating to roughly 4.4 light years. Even with our absolute best current space travel technology, 70,000 years is the ETA for just the closest star system to our own.
It really underscores the massive challenges of true interstellar travel. Now, thinking about our own broadcasts compared to the galaxy should humble absolutely any pilot. Our maximum comms range is virtually undetectable. I mean, it's a mere whisper against the howling cosmic wind of our home galaxy. The human radio bubble is a tiny sphere extending just 100 light-years around Earth. It contains literally every radio and TV broadcast we've ever beamed out into the dark. But the Milky Way? It's a vast spiral spanning 100,000 light-years in diameter, packed with hundreds of billions of stars. Any civilization living just outside that 100 light-year bubble is completely oblivious to our existence. To them, it's as if humanity never even existed.
Leaving the Milky Way in the rear view, we reach Phase 4, intergalactic macrostructures. Our flight path now requires us to truly comprehend the towering architecture of the cosmos itself. We are entering intergalactic space now, a completely silent expanse, an unimaginably vast wilderness between the islands of galactic light.
Let's track this hierarchy outward. As we zoom out, our entire galaxy becomes literally nothing more than a microscopic speck within Laniakea, which is this gravitational masterpiece bound together in a vast cosmic web. First up, we have the local group, a neighborhood of over 50 galaxies spanning 10 million light-years. Then, that group is just one tiny part of the Virgo supercluster, a massive structure 110 million light-years, or 33 megaparsecs in diameter, containing thousands of galaxies. And incredibly, even the Virgo supercluster is completely swallowed up by the unimaginably massive Laniakea supercluster.
Laniakea actually translates to immense heaven in Hawaiian, and it contains the mass of 100 million billion suns. At the heart of this immense heaven lies the Great Attractor, a highly mysterious navigational hazard exerting a massive gravitational pull on everything within our supercluster. The sheer scale of Laniakea, spanning 500 million light-years, provides a profound context for our existence. In this grand cosmic library, our entire recorded human history is just a single sentence, on a single page, on a single planet, within a tiny component of a gigantic structure.
And now for our final waypoint, Phase 5. Edge of observable space. We are pushing our sensors to the absolute limits of what reality allows us to see.
At this extreme edge, our telemetry systems are presenting a total paradox regarding the true, potentially infinite size of the cosmos. Our sensors map the observable universe at roughly 93 billion light-years in diameter, yet the universe itself is only 13.8 billion years old since the Big Bang. What actually lies beyond this observable 93 billion light-year perimeter? Well, that remains one of the absolute greatest mysteries of cosmology. The true size of the entire expanse remains utterly unknown to us.
I'll leave you with that provocative thought to ponder on your journey, pilots. If the universe is only 13.8 billion years old, how can it be 93 billion light-years across? How can it be so vast in so short a time? Well, it's because cosmic expansion is stretching space itself. Space is actually expanding so rapidly that some regions are moving away from us faster than the speed of light. Because of this, there are entire galaxies out there retreating into the dark that we will never ever get to witness. They are placed forever out of our view. Safe travels out there, pilots. Keep your eyes on the stars and always remember the staggering scale of the cosmic ocean you are navigating.